Hello everybody and welcome to a new problem from the strings chapter. This one is called Palindromic Substrings, and our job is that given a string, we have to count how many palindromic substrings there are in the string. The substrings with different start or end indices are counted as different substrings even if they consist of the same characters. So, let's take a look at these examples. On the first example, we have a string of length 4, A, and it contains 9 palindromic substrings. As you can see, all the characters in this string are equal, so each and every substring is indeed going to be a palindromic one. So, we have 4 palindromic substrings of length 1. And as you can see, all of them are equal if you compare them as strings A, and A. But if you compare them as substrings, which mean what is the start and the end indices of them, they are distinct. The first one, for example, is the substring 0, 0. So start index equals end index equals 0. And the second one is 1, 1. This one is 2, 2. And this one is 3, 3. So this is why they are considered distinct. And we are going to count each and every one of them. Right. Now, of length 2, of course, we have 3 of them. This one, this one, this one. So another 3 palindromic substrings. Of length 3, we have 2 of them. And of course, of length 4, we have the whole string. This is a total of 9 palindromic substrings. Now, if we take a look at the second example, our string is ABCBA and it contains 7 palindromic substrings. And let's see what are they. Obviously, each substring of length 1 will be a palindromic one. So we have 5 palindromic substrings of length 1. Then, if we take a look at the substrings of length 2, well, none of them is actually a palindromic one. If we take a look at the substring of length 3, we have 1, which is a palindromic one, BCB. And if you take a look at the substrings of length 4, none of them is a palindromic one. And the only substring of length 5, which is the whole string, this is a palindromic one. So this is why the answer is 7. Awesome. And the first thing that should come to your mind right now is that this is a problem where we need to compute the number of valid substrings, where a valid substring, of course, has some definition, right? It is the same as the problems where we had to compute the number of valid subarrays, or the problems where we had to find the longest valid subarray. And yeah, we always can come up with a brute force approach for this type of problems. And the brute force approach consists of trying out each and every substring, check if that substring is a valid one, and if so, just increment our answer. So, the first stage, try out each and every substring. A substring, of course, is determined by the start and the end indices. We are going to note them by I and j, where of course I is less than or equal to j. And for each pair of indices I and j, we have to check if this substring is a palindromic one. And how should we do that? Well, obviously we have already solved this problem. It is the problem palindromic string, and all we should do is apply that algorithm, but not for the whole string and just for the substring I, j. So let's say I'm going to write the function where of course I'm going to have the code from palindromic string. If is palindromic of, let's say, s, I, and j, if this substring is indeed a palindromic one, all I need to do is, of course, increment the answer. So answer plus equals 1. And that's it. And this is how the code for our brute force approach looks like. We are going to use a variable to store the answer, which is initially 0, and is going to be returned in the end. Then we are using 2 nested for loops to try out each and every substring. So the start index I from 0 to n-1, the end index j starting from I to n-1, and of course we check if it is palindromic, and we increment the answer. Awesome. Now, let's analyze the time complexity of this brute force approach. Of course, we are going to start with the constant operations, right? Return is constant, the increment is constant, and the initialization is constant. Awesome. Now, what happens here is that we have to start from the bottom, and the bottom is actually this piece of code. And what we care about here is indeed the function call, right? If you remember, we have solved the problem palindromic string in big O of n time complexity and big O of 1 memory complexity, where n was the length of the string that we wanted to check. Here, we want to check a substring which is of length j minus I plus 1. So the number of iterations this function call will do is j minus I plus 1. Awesome. Now, of course, this number of iterations depends on the value of j, which is in this for loop, and the values that j will take also depends on the value of I, which is from this for loop. In theory, we should take all the values for I and j and add this number to a sum, compute that sum, and that will be our time complexity. But we have already tried to do that in a problem in the arrays chapter. The sum is going to be very hard to compute, so no need to do that. All you can do here is take the upper bounds and multiply them together, right? So this j minus I plus 1, which is the length of my substring, is going to be, of course, less than or equal to n. In the worst case, we are going to check the whole string. Then this j that starts from I and goes all the way to n minus 1 will take less than or equal to n values. And of course, I will definitely take n values. This we know for sure, right? So we can multiply these three together and we can conclude that our brute force approach has a time complexity of big O of n cubed, and extra memory, any extra memory, well, doesn't look like it. Constant extra memory. Now, this is definitely very slow, but it is good for a brute force approach, it's good for start, and what we want is to optimize this big O of n cubed time complexity to a big O of n squared. So, think about this, and we are going to discuss it in the next solution.